Hi grade 10s and welcome to this video. In this video, we will be working on the Mathematics Paper 1 for June 2023. And this paper is specifically from the Gauteng province. The time allocated to this paper is an hour and we have 50 marks. So moving on to the instructions, just keep in mind that there are a total of 5 questions in this exam paper. Make sure to round off your answers to 2 decimal places unless stated otherwise, and the diagrams are not necessarily drawn to scale. Okay, so with that being said, let's get into question 1. Question 1 says, determine the following without the use of a calculator. So 1.1 says, between which 2 consecutive integers lies negative square root 69. Okay, we need to take note that this number is negative, but because we have the square root, okay, we're going to look for square numbers that lie between 69, okay, because we are square rooting this, right? It's the square root of 69, but specifically negative and then square root 69. So this becomes negative at the end of the day. And we need to think about an integer value that would be less than this, and then one that is greater than this. Okay, so that the negative square root of 69 is greater than that number, but less than this number. Okay, because these have to be integer values, right? When comparing them, we can find the square root of perfect square numbers that lie right between this number 69. Because perfect square numbers will be the only ones that get square rooted and then they become an integer value. Okay, but there's something else we need to take note of here. This is negative. Okay, so with negative and positive numbers, they work a little differently. If the number is, I'm speaking about this part, right, under the radical, the bigger that number is, then if it is a negative number, the smaller it will be. If we have some numbers here and they're all negative, right, we can have, for example, negative 4, negative 6, and negative 1. Which would be the smallest? It would be negative 6. Despite the fact that it has 6, which looks to be the biggest number here. But because it is a negative number, it's more to the left. Okay, so just keep that in mind. So this would be, the number that comes under there would be a number bigger than 69. Okay, so let's think about a square number bigger than 69. That would be a square number immediately bigger than 69 would be 81. Because after 60, we have 70s, and we know there's no square number in the 70s. But then we have 81. The square root of 81 is 9. So we'll have 81 here, but remember it is negative. Okay, so it counts as a smaller value to this. And then here, we're going to have, compared to 69, it should be a value that is less than 69. So think about a square number that is less than 69. Okay, so in the 60s, we have 64. Okay, before 49, so 64. And so this would be negative square root of 64. Okay, so we can already see what they're going to be. This is going to be the negative square root of 69 is greater than, and the square root of 81 is 9, so negative 9, but less than, and the square root of 64 is 8, so less than negative 8. And there we go. These will be the 2 integer values that this surd lies in between. Okay, so just really think about the numbers and how numbers work when they are negative. So you can just conclude this, okay, between negative 9 and negative 8, and that is our answer. Moving on to the next question. And then question 1.2 says, show that 0.9 recurring equals 1. Okay, so this is a question that is asked a lot here and there. Just keep in mind how to do this. It's also a question that is worked on in the first sections of your textbook, okay? So it is 0.9 recurring, which looks like this, 0.999, and it just continues. And we need to show that it's equal to 1. So the way we can do this is to convert this into a fraction. And then you'll see that that fraction will be equal to 1. So here's how we work with this. We are going to take this number, 0.9 recurring, and we're going to say, let this be equal to x. Okay, let x equal this. And the whole goal here is we need to get rid of this 9 recurring. Okay, we need to get it out of the way. Now, the way we can do that is to create a new equation, which is also going to have 9 recurring. So to create that new equation, we can take this and simply move a decimal up. So this will be 9.999, so 9 recurring. And the whole point of that is just to isolate that 9 recurring, since we know that 9 continues forever. So we need to move one decimal place up. The way we can do that is by multiplying this by 10. So we're really just taking this equation, x equals 0.999, and we're just going to multiply both hand sides by 10. So we can call this equation number 1 if you want to, but it's not really necessary. You can just say if x is equal to this, then multiply both hand sides by 10. It would mean that 10x, because 10 times x is 10x, is equal to, and when you multiply this by 10, it's going to cause that decimal to move one place up. And so we have 9.999, and that is also recurring. And here we have isolated this 9 recurring, and now we can actually deal with it like this. We are going to take this equation with 10x, right, and subtract it by x. So we took the left-hand side minus the left, so you also have to say the right-hand side minus the right. So that means 9.9 recurring, okay, minus 0.9 recurring. And do you see how that 9 recurring will leave? Because that 9 continues infinitely. This 9 also continues infinitely. But now we're saying this minus that. So those recurring 9s, they cancel. And so we have 10x minus x, which is 9x, is equal to 9 minus 0 is simply 9. And then solve for x, okay? Because we're trying to find x, which is 0.9 recurring. And so divide both hand sides by 9. And do you see now how x is simply equal to 1? So therefore, 0.9 recurring is equal to 1. And there we go. Okay, so that is it for that question. And that is it for question 1. Question 2.1 says factorize the following expression. And we have an expression with 4 terms, which should immediately make you think about grouping. Okay, so we can just start by grouping the first 2 together and then the last 2 together. Do you see how the first 2, they have a 3 and an x in common? Okay, so 2 things in common here. These ones have a 2 and a y in common. So we group those 2 together and then take out your common factor. So in the first and second term, we have 3 and x in common. And then when you open your bracket, what is left? What do you multiply to 3x to get back to 3x squared? You would multiply by x. And then what do you multiply to 3x to get back to 9x? You'd simply multiply by a positive 3. Okay. And now in the second term, what do we have in common? We have a negative 2, we have a negative 6. So there's a negative 2 first, and then a y and a y. So y is common. Then what do you multiply to negative 2 to get back to negative 2xy? You'd multiply by x. And then what do you multiply to negative 2 to get back to negative 6y? You'd multiply by positive 3. Okay, because if you say 3 times this, that becomes negative 6 and y. So do you see how we have the exact same bracket now? So what we currently have is we have 2 separate terms. Remember that terms are separated by plus or minus signs. So this is one term and this is another term. And in these 2 terms, we have a bracket in common. So we'll take that out as a common factor. And what is left in the first term? If this bracket comes out, what you multiply to this to get back to all of this? You simply multiply by the 3x. So times 3x. Again, you have this. You can actually just see it as all of this divided by that. And so you can see what is left. It's just the minus 2y. And there we go. Okay, so it's done. There are no common factors between the numbers in each bracket. And so that is it. Moving on to the next question. The next question, we have to simplify this expression where we have m squared minus 64. Do you see that we have a squared value, a squared number, and a minus in the middle? Meaning we can use difference of 2 squares. So we open up 2 brackets and we have m multiplied by m. And then 64, the square root of 64 is 8. So we have 8 times 8. And then you just say plus and minus. And then all over, and look at what we have here. That is not difference of 2 squares because we are using a plus. Yes, this is a square number, but you see, that's also not really a square value. So we can't really say that. So no difference of 2 squares here. But do you see that it has 2 terms? And in each term, there is an m that we have, which is common. So we're going to take m out as a common factor. And then what are you left with? You can simply say m squared divided by m. And you see what is left. It's just m. And then 8m divided by m, you're left with positive 8. Okay, so you see what's going to happen there. Then we are dividing. Now, when dividing by a fraction, you can use this simple rule called tip and times. With tip and times, we tip the fraction. Okay, so you say divided by whatever fraction we are working with, we tip that, meaning swap its numerator and the denominator. So now it's m over m minus 8. And then times, you turn its division into a multiplication. Okay, so here we are. Now, in the first fraction we have, you can see that m plus 8 is common. So these are multiplying, these are multiplying. We can't cancel when there's a plus or minus sign immediately there, but when we have brackets and we are multiplying all through, then we can. So m plus 8 will cancel with m plus 8, and then all we are left with here is m minus 8 over m. And then we are multiplying by m over m minus 8. And so do you see what's going to happen here? Because we can cancel numerator and denominator, when you're multiplying, you can also cancel diagonally with the numerator and denominator. This is because when they multiply, you're saying m minus 8 times m. You're going to get m times m minus 8. And here, m times m minus 8 is also m times m minus 8. So do you see how they would cancel? That cancels with that, and that cancels with that. So immediately, you can just cancel it like that, and like that. And what is left? When these cancel, okay, we're just left with 1 because what was common just cancelled. And so you saw how when they multiplied, okay, you see why it cancels perfectly because it's just the same thing in the numerator divided by the same thing in the denominator. So this is equal to 1. And that is our answer. Okay, moving on to the next question. The next question, we have an exponential expression. So in this expression, do you see the bases we have? 2, we have 8, we have 16. What did they all have in common? They can all be expressed as a base of 2. So that's what we're going to do. The 2 is still just 2, so to the power of n minus 1. Then multiply by 8 can be expressed as 2 to the power of 3. But then it's still raised to the power of n plus 1. And then all over, and we have 16, which can be expressed as 2 to the power of 4. Raised to the power of n, of course, when they multiply, that just becomes 2 to the power of 4n, okay, because the 4 and the n multiply. And then let's just multiply there. So we have 2 to the power of n minus 1 times, now you're saying this value raised to this exponent. Just like if you say 2 raised to the power of 2 is actually 2 squared. The reason why is because there's an exponent of 1 here, and so those exponents multiply. This is the power law that you learn in your laws of exponents. So we have 2 raised to the power of, and 3 times n is 3n, and 3 times 1 is positive 3. And then all over, we still have the 2 to the power of 4n. Okay, now in the numerator, we have a base with this exponent times the same base with another exponent. When your bases are the same and you're multiplying, okay, you need to add your exponents. So the base will stay the same, but add the exponents. So this is n minus 1 plus 3n plus 3. And then all over 2 to the power of 4n. And so when we add here, n plus 3n just gives you 4n. And negative 1 plus 3 is 3 minus 1, which is just positive 2. Okay, so now we can divide. You see, you could have split these up if you wanted to. It can be 2 to the power of 4n and then break it up. How we can split that up is 2 to the power of 4n times 2 to the power of 2. So it will hold the law that says that if the bases are the same and we are multiplying, you add the exponents, okay? So it will be 2 to the power of 4n plus 2. And then all over 2 to the power of 4n. And you see what is common would cancel. So it divides and becomes 1. And then we have 2 to the power of 2, which is equal to 4. And it's in the exponent, so it's really just 4 over 1, which is 4. And that is our answer. Okay, and that is it for question 2. Question 3 says, solve for the unknown variable in each of the following. Okay, and 3.1 has a interesting looking equation for grade 10. But if it looks intimidating, it probably means it's actually very simple because they won't give you, what we will call cubic equations. They won't give you those in grade 10. That is introduced in grade 12. So this means this is actually really simple to work with. You have this binomial, okay, an expression with 2 terms, and then multiplied by a trinomial. But you notice something about this. once you FOIL out here, when you multiply a times a squared, you're going to get an a to the power of 3. And when you multiply here, you're also going to get an a to the power of 3. And then when you transpose it, that a to the power of 3 is going to leave. Okay, so it's not something to worry about. It will probably end up being either quadratic or linear. So let's just go ahead and distribute. So we multiply in and we get a to the power of 3. And then we get 2, positive 2a squared. And then lastly, a times negative 3 is minus 3a. Okay, and then the 1 with everything else. And of course, all of those will just stay the same. So it's going to be plus a squared plus 2a minus 3 is equal to, and distribute here as well. So this is a to the power of 3 and plus 3a squared. Okay, so you see that a to the power of 3 and a to the power of 3, they would cancel because you would take 1 over. Okay, and let's just simplify what's on the left. So you have a 2a squared plus an a squared, and that gives you 3a squared. So you see something else that will also cancel. And then an a and an a, so that's going to be negative 3 plus 2 is negative a left that we have. And then we have minus 3 equals, and then 3a squared. If you transpose again, if you take that over or this over, they will cancel. So let's just go ahead and say we take all of these over to this side. So they become negative or positive, just depending on whatever their sign was. So this is just going to be 3a squared, and that comes over to become minus 3a squared. And so you see how they cancel. So once you see they're exactly the same, you just cancel them out. And now let's just go ahead and isolate. So you see you're just going to have an a and a 3. Let's leave it as negative a is equal to, and take that 3 over, so it becomes positive 3. And then you can just divide both hand sides or multiply both hand sides by minus 1 to make the a positive. So finally, a is simply equal to negative 3, and that is our answer. Okay, moving on to the next question. The next question, you are given a quadratic equation. So it's that type that has a coefficient in front of x squared that is not a common factor, clearly. And so we have to factorize. So you can use any method that you are comfortable with. I'm going to use a method here called the cross method. So we're going to take the first term and get the factors of the first term, which is 2x multiplied by what gives you 2x squared multiplied by x. And then factors of the last term. The last term, 3. Okay, 3 is a prime number. So it's just going to be 3 and 1. But of course, this is negative 3, so one of it needs to be negative. Now, we need to give the negative to one of it in such a way that once we multiply and add the products, they give us a positive x in the middle. So instead of playing a guessing game, what I'm going to do is find those products first. So 2x multiplied by 1, this is why it's called the cross method, because we multiply across. So that gives us 2x, and then x times 3, that gives us 3x. So which should be negative so that you end up with a positive x? You should give the negative to the 2x, okay, to the smaller value. So when you say negative 2x plus 3x, it will give you positive x. And so the factor that takes the negative is going to be whatever created the 2x. When we say 2x times 1, that's what created 2x. So give that negative to the 1 and the positive to the 3. Okay, so there we go. Open up two brackets and we are factorizing. So 2x plus 3, and this is x minus 1, and those are our factors. Okay, so finally just solve for x. We are saying something multiplied by another thing gives us 0. Therefore, it's either the first is equal to 0 or the second is equal to 0. And that way, when they multiply, they give us 0. That's what makes the left-hand side equal to the right-hand side. So we say 2x plus 3 is equal to 0, or x minus 1 equals 0, and then solve for x. Here, we need to transpose the 3, so it's going to be 2x equals negative 3. Then divide both hand sides by 2. And finally, x equals negative 3 over 2. Or here, just transpose the negative 1. So x is equal to 1. And these are answers. Moving on to the next question. The next question gives us a linear inequality to solve for. And so we need to isolate x. So we have a 2x minus 1. And so to get 2x alone first, we need to take the 1 over. But this is an inequality that's really just two inequalities that has been grouped as one. Okay. So to do that, you need to take the negative 1 over on both hand sides. So we have 2x is greater than or equal to, and that's going to be 3, and that comes over, it's negative, so it comes over to become positive 1. And so 2x is greater than or equal to 4, but less than, and we had a 7 here, but that comes over to become a plus 1, so we have an 8 now. Okay, and now solve for x. You see that to solve for x, we need to get rid of the 2, so we'll divide all sides by 2. So finally, x is simply greater than or equal to, that gives us 2, and that is 4, so less than 4. And that is our answer. X is greater than or equal to 2, but less than 4. Moving on to the next question. The last question is a simultaneous equation, and we need to solve for x and y simultaneously. Now, this one works a little different to the ones that you've always been working on because we have exponential equations here. But the thing about exponential equations is, for example, let's say you're given something like 2 to the power of x is equal to 8. The goal of this exponential equation, or to solve for x really, you need to ensure that the bases are the same. Because this is 2 to the power of x, if you can find out 2 to the power of what this is, then for the left-hand side to be equal to the right-hand side, their exponents should simply be equal. So you know that 2 to the power of 3 gives you 8. So that means x should just be equal to 3. And then that would be your solution for x. In the same way, we're going to do the same thing here. So here we have a 3 to the power of x plus y equals 27 to the power of 2. And then we have 2 to the power of y equals 4 to the power of x plus 1. Which do you think we can work with? Well, they both have x and y, so it's fine, regardless of which one you work with. So with both equations, what's going to happen is they're both going to become linear, okay? Because do you see that the variables are in the exponents? So we can actually just work on both of them at the same time. That's fine. So we can start with this one. That's fine. This is 3 to the power of x plus y equals, and then 27 to the power of 2. We just need to ensure that there's a base of 3. So how do we do that? 27 can be written as 3 to the power of 3. And then that is raised to the power of 2. So then the 3 times the 2 multiplies, and then we have 3 to the power of x plus y equals 3 to the power of 6. And there we go. Our bases are the same. Therefore, for this equation to be true, the exponents should be equal. So the equation we get now is x plus y equals 6. Okay, and now we can form our next linear equation with this. So here, we need to ensure that the bases are the same. So this is 2 to the power of y, and that can be 2 to the power of 2. That's what gives us 4. And then it's raised to the power of x plus 1. So 2 to the power of y equals 2 to the power of, and you saw with the exponentials, what happens here? This is 2 to the power of x, and then that multiplies to become plus 2. Okay, and now that the bases are the same, the exponents are equal. So y equals 2x plus 2. So do you see the two equations you actually have? They are two linear equations, and you can solve for x and y. At this point, I'll just call this equation number 1, and this is equation number 2. So we just took those ones further, okay? And now, because this says y is equal to, I'll go ahead and take this and substitute it into that equation. So I'm going to take equation number 2 and substitute it into equation number 1. So wherever you see y in equation 1, replace it with 2x plus 2. So we have x plus y. So that's x plus, and there's y. So replace it with 2x plus 2 equals 6. And now we simplify. So this becomes 3x. And you see, you can just take the 2 over. So x is on one side, numbers on one side. So when it comes over, it becomes a minus 2, which gives us a 4. Then divide both hand sides of the equation by 3. And finally, x is simply equal to 4 over 3. Okay, and now we can solve for y. Now that we know x, just look for the equation which had y as a subject. So there we go, y. So we'll say y is equal to, and we have 2 times x, which we know is 4 over 3, plus 2. And then just solve for y. Y equals C2, and the 4 multiply because they're in the numerator. This has a natural denominator of 1. So that is 8 over 3, and then plus 2. So to add these, you can ensure that the denominators are the same. To make a denominator of 3 here, you'd have to multiply numerator and denominator by 3. This has a natural denominator of 1, so it's just going to be 6 over 3. Okay, so 8 plus 6 gives us 14, and then over 3. And that is our answer, which of course you could have used the calculator. But, it's good to not depend on the calculator so much. So that is our answer, x equals 4 over 3, and y equals 14 over 3. And that is it for question 3. Question 4 says the graphs of f of x, which is equal to 2x squared minus 2, which is our parabola, and g of x, which is equal to negative k over x plus 1 and 1 over 2. Okay, this is a mixed fraction. You can just turn it into an improper fraction. 1 plus a half is 3 over 2. So instead of this, I will just use 3 over 2. Okay, and then they tell us that a and b are x-intercepts of f, and then c is the y-intercept. Okay, and d, negative 2 and 6, is a point of intersection between the two graphs. The first question in 4.1, we have to write down the domain of G. Okay, so the domain of G, look at the graph of G. That is your hyperbola. So with the hyperbola, the domain is going to be a specific thing in grade 10. Okay, this changes in grade 11 because they're going to show you that we can actually have a shift here. Okay, a horizontal shift. So it's going to be a bit different there. So think about what domain is. The domain refers to all the possible x values that a graph has, okay, or can have. Let's look at the graph of G. So with this graph, do you see that if you map all these points to the x-axis to understand the x values that this graph will have, look at all the x values it has. This point has an x value over here. This point has an x value over here. It has x values almost everywhere, okay? As it maps to x values all through. Even as this graph moves closer and closer and really just comes from being really close to this asymptote, okay? Do you see that it's going to have x values that extend to negative infinity and even positive infinity? There's just one place it will not have an x value. So it has all these x values, negative 3, negative 2, negative 1. But then here at 0, look at what happens. Do you see how this graph moves closer and closer to the y-axis? And the y-axis is this point where the x value is equal to 0. Okay, here the x value is maybe negative 1. It's probably here though. Okay, so it's not going to have an x value at 0 where x is equal to 0. And you can see that from the equation now. What happens if you make x equal to 0? Okay, the value of this function would be undefined because the denominator is equal to 0. So what do we say is the domain of G? We say that the graph of G, its domain is x can be any other real number. So x is an element of all real numbers, but x is simply not equal to 0. And that is our answer. Moving on to the next question. Question 4.1.2 says we need to determine or write down the range of f. Okay, so the graph of f is our parabola. What is the range? The domain refers to all the possible x values of a graph. The range refers to the y values. So what are all the y values that exist for this parabola? Well, with a parabola, because they're referring to y values, okay? When they refer to y values, you can look at the y-axis and then just see the y values that this graph would have. See, this point over here, it has this y value. And of course, this point has the same y value, okay? And then this point over here has this y value. This point has this y value. As we keep going lower, you see there's this point here. After this, we don't have y values down here, okay? So we would have to find out what is the y value here at this point, which is also called the turning point. And then all the y values that exist for this graph would be values that are either equal to this y value or greater than this y value, because it has y values all through, even heading to positive infinity, since your graph is going to extend up like that. So it has y values all through there. Okay, so our goal is to find out what is this turning point. You can see that the turning point is also the y-intercept, okay, in grade 10, of course. This is going to change a bit in grade 11. So this is the equation of your function. How do you find the y-intercept? You find the y-intercept because this is the point where x is equal to 0. You simply make x equal to 0. So we're going to take the graph of f and say f of 0, but you don't really have to do that because it is, okay, that stands for your y-intercept. If you make this equal to 0, everything becomes 0. But yeah, you can show them your calculation. You can say I said f of 0 equals 2 times 0 all squared minus 2. And so f of 0 equals negative 2. So you know what that y value is now. This is minus 2. And so it means that all the y values that exist for this graph are values that are either equal to negative 2 or greater than negative 2. And so how you write this down is y is greater than or equal to negative 2. And that's of course writing it as a set in set boulder notation. We can write it in interval notation, and that would look like this. We would say y is an element of. Now with this notation, you're going to have to think about where you're starting from and where you're ending. The starting point should be the smaller number and the ending the bigger. This case, we are saying we have negative 2, okay? And we are saying its values that are greater or equal to negative 2. So equal to negative 2 or greater than negative 2. So in this case, we have negative 2 and the number we are heading to is positive infinity. So you're going to say y is an element of negative 2 to positive infinity. And here we said it is equal to or greater than negative 2. So because it's equal to, you use a square bracket to show that negative 2 is an included y value. But of course, infinity is not a fixed value, so you use a round bracket here. Okay, so these are the two ways to write this answer. You can leave it like this or like that, and it's perfectly fine. Moving on to the next question. The next question says determine the equation or write down the equation of the horizontal asymptote of G. The horizontal asymptote. So with the horizontal asymptote of G, the hyperbola, remember that the hyperbola's general form is y equals a over x and then plus q. This is the value of your horizontal asymptote. The equation of it is always y equals whatever that q value is. Okay, it is a horizontal line. That's why it's called y equals. So it's a line that passes one particular y value on the y-axis. Okay, so as you can see, if you put this in this format, k is your a value, and then you can see that x, okay, and then this is plus q. So it's 3 over 2 or 1 and 1 over 2. So you can simply say the equation of the horizontal asymptote is y equals 1.5, or I would actually just write it as y equals 3 over 2. Okay, so like this or like that, it's fine. Okay, moving on to the next question. Question 4.2 says calculate the length of AB. Length of AB. Okay, you see that to find the length of AB, you need to find A and then B, and then you can see the length of AB. So A and B, they are the x-intercepts of our graph of f, our parabola. So how do you find the x-intercepts when given the equation of a parabola? By making y equals 0. Because at this point, this is on the x-axis. The y value is 0 and the x value is negative, whatever that is. Okay, so just take your function and then make y equal to 0. Okay, so make y equal to 0, which is f of x. So 0 equals 2x squared minus 2. And then we can transpose the 2 to make it positive. So 2 equals 2x squared. Get rid of the 2, divide both sides by 2. Therefore, x squared, okay, is equal to 1. And then solve for x. This is an equation, so we can square root both hand sides to get rid of the squared. But remember, it's an equation. So the positive and negative solution should be considered because we are saying something squared is equal to 1. Well, 1 squared is 1. But negative 1 squared is also 1. You need to consider all the real solutions for this equation. Okay, so finally, we'll just say x is equal to positive 1 or x is equal to negative 1. Okay, and so you can see that that means that the coordinates of A, okay, that's the one on the negative part. So that's the negative 1, that's the positive 1. You can already see the length. So this is just the x value of A and that's the x value of B. And so to find their length, you can simply just say, okay, from the origin, I went 1 unit to the left. And from the origin, I went 1 unit to the right. So that is exactly 2 units. Okay, so it's just 1 plus 1. Or you could say higher x value minus the lower x value. So finally, to find the length of AB, it's equal to 1 minus negative 1. Okay, higher x value minus the lower one. So AB is simply equal to 2 units, okay, because those negatives multiply in to become a positive. And that is our answer. Moving on to the next question. The next question says, show that k is equal to 9. Okay, so they've already told us what k is. We just need to show them. You see, in the equation of g, right, the only thing missing is k, because x and y are supposed to stay like that. So if you had one point with an x value and a y value, it will form an equation that solves for k. So that's what we're going to do. Look at your graph of g, and do you have a point on this graph which you can use? Yes, we do. We have d, okay, which is -2 and 6. So put down the equation of g and then substitute that point. So remember that d is -2 and 6, and we're going to just put this in place of x and y. Remember, this is 3 over 2. So we have the y value 6 is equal to negative k over, and we have -2 here, and then plus 3 over 2. So this will just become positive k over 2, and we can just take that over. So that is 6 minus 3 over 2, okay? So 6 minus 1.5, that is already 5, and then 4.5. So that is 9 over 2 is equal to, and we have k over 2, okay? You can already see what k is. If you just finally get rid of the 2 by multiplying both hand sides by 2, but you can see, of course, the denominators are the same. So, of course, the numerators are the same for this equation to be true, for the left to be equal to the right. So, finally, k really is equal to 9. And that is our answer. Moving on to the next question. Question 4.4 says, write down the equation of the line of symmetry of G with a positive gradient. Okay, so the line of symmetry of G, which is a hyperbola. Let's speak about hyperbola's line of symmetry. A hyperbola has two lines of symmetry. So our graph currently looks like this and like that. Okay, of course it crosses over like that. With this graph, we have two lines of symmetry, two lines that cut the graph symmetrically. So it makes this part look exactly the same as that part. Okay, it's like a mirror image, like this has been flipped over to look like that. And so this one is a line that is going down. So this is the one that is a decreasing function. And if a line is going down or is a decreasing function, it means that the gradient of that line is negative. So this is the one with a negative gradient. And then, of course, we have the one with a positive gradient, which would look like this. See how this line divides this graph symmetrically, how it makes this part of the graph look exactly the same as that part. And this line is the line that is increasing, it's going up, okay? So that would have a positive gradient. And this is the one we're looking for. Now, to remember the equation of the line of symmetry, it's very simple. If you remember the general equation of a hyperbola, you'll remember that equation. So the hyperbola's equation is y equals a over x and then plus q. The equation of the line of symmetry with a positive gradient is y is equal to x plus q. Done. Okay, just that part. And then the one with the negative gradient is very simple, just y equals negative x plus q. Okay, so we can see what we're looking for. And all we need is the value of q. So take that, get your value of q. Y equals x, and then what was q? Again, we saw it was this last part, which was plus 1 and 1 over 2, which is 3 over 2. So y equals x plus 3 over 2, and that is our answer. Moving on to the next question. The next question, question 4.5 says, write down the value or values of x such that g of x is greater than f of x. So remember that this refers to the y values of these graphs. So where are the y values of g greater than the y values of f? How can you determine when a graph's y values is greater than another graph's y values? Well, y values lie on the y-axis. So let's say we had a graph, and let's just call that g, okay, a straight line. And then we have another graph, and let's call that f. Where the y values would be greater than the y values of f would be, you'd have to look at it like this. You see, let's take this point, for example. Okay, the point where they intersect. Do you see that they have the exact same y value? Okay, they intersect, so they have the same y value. Now, if we move this side, okay, to the left, do you see how the graph of f, the red graph, has a higher y value than the graph of g for this particular x value? Okay, this one is maybe something like 1, and this one's like -1. Okay, the graph of f has a greater y value than the graph of g here. But that does not meet what we're trying to find. We're trying to find where the graph of G has higher y values than the graph of F. So in this region, this is where the graph of F was above the graph of G. What you need to look for is where the graph of G is above the graph of F. That way, the y values of G will always be greater than the y values of F for each x value that we look at them for. Okay, so that's what we're going to do. Okay, so let's go ahead and look at our graphs and just see. We're looking for, just remember, G must be greater than F. So we're looking for places where the graph of G is above the graph of F. Okay, so let's go ahead and highlight the graph of G in blue and the graph of F in red. Now, where do you see the graph of G being above the graph of F? You can use a ruler. And the reason the ruler method works is because with a ruler, you're always comparing it to the same x value. Okay, so this x value, for example, do you see where the graph of G is? It's over here. And look at where the graph of F is. Now, we'd have to extend this graph of F. It's way up there. So do you see that here? This is where the graph of G has a lower y value than the graph of F's y value. Because the graph of F will have a high y value way up there. Okay. So then you'll take your ruler and then you start moving to the right and just see, where does this happen? Again, here, the graph of F is still above the graph of G. Okay, it has a higher y value than the graph of G's y value. This is higher than this. So that doesn't work there. So you always need to now look for the point of intersection. This is where the change happens. You see that at this point D, this is where they have the same y value. They have a y value of 6. Then after D, what happens? The graph of G, the blue graph, now has a higher y value than the graph of F, and that's what we want. G of X must be greater than F of X. Okay, so just monitor it all through. You see, the graph of G is above the graph of F, all through here, right? And then what happens? We have an asymptote, so then it cuts off there. The graph of G cuts off. So we can see that it works here. We can highlight that first. Works all through here. And then the cutoff point is by that asymptote at x equals 0. Okay, so I've highlighted that there. And then if we keep moving, what happens? Do you see that now the graph of F is above the graph of G? We don't want that. And all through the graph of F is above the graph of G, and it doesn't work all through there. G must be above F. So we can see that it only happens here, starting at immediately after that point of intersection of -2. So that's going to be from -2 all the way to the x value of 0. So if you line all of these, okay, the values of x for which this highlight exists, you see that it's all of these numbers from greater than -2 but less than 0. And so how we answer them is we simply say this is where x is greater than -2 but less than 0. And that is our answer. Okay, you can also, of course, write this in interval notation, which is x is an element of, and you're going from -2 all the way to 0. But it's not greater than or equal to -2, it's just greater than -2. So use a round bracket here, also round bracket here. So you can write it like this or like that, and it is perfectly fine. Moving on to the next question. The next question, 4.5.2 says, we need to write down the values of x such that both F and G increase as x increases. Now, they didn't really need to say as x increases. It's just really we're looking at the values of x for which both F and G are increasing. Remember what it means for graphs to increase or decrease. We saw that with a straight line. If a graph is an increasing function, it's moving up. Okay, so it's going up. So when they say as x increases, they're just saying you're looking at it from left to right, because the numbers from left to right, they increase. For example, you have something like -3, -2, -1, 0, 1, 2. We're increasing, okay? So that's what they mean. The graph of F and G must both be increasing as x increases. Okay, let's just see where that happens. And of course, they need to work for the same x values. Okay, let me erase all of this. Okay, so we need to see where they are both increasing. Let's monitor the graphs all through. So with the hyperbola, you're going to notice something with that. You see, if you look at the hyperbola from left to right, look at what it's doing all through. What is it doing? It is increasing. Okay, even on this side, it is increasing. That's what's going to happen if a is less than 0. Okay, that value of a up there. Okay, it was a negative value. So you see how that affects the graph. So it's increasing all through. But then now the graph of f needs to be increasing for the same x values as well. Okay, so where is the graph of f, the parabola, increasing? Look at what it's doing here. Here it is going down. It's decreasing. We have to look at it from left to right as the x values increase. So here it's decreasing, and then it reaches a turning point, and then it starts increasing. So we just need to tell them the values of x for which they are both increasing. From this, because this part is decreasing, you see how you can't take anything here. Because here, this is decreasing, but this is increasing. That's not what they want. They want them to be both increasing. So we're going to have to look at this part over here and tell them the values of x for which these sections of the graph both exist. So for which they both exist, looking at that, if you line them to the x-axis, do you see that it's values that are immediately greater than this x value of 0? See, it's all of these values here. If you line it up to the x-axis, all of these values, even, these ones here, these are all values that are simply greater than 0. This is where they will be increasing. That will shoot up forever. That will shoot up, moving closer and closer to that asymptote, never touching it. Okay, so that is our answer. X is simply greater than 0. Okay, so that is our answer. We'll just tell them x is greater than 0. Of course, you can write it in interval notation, which is x is an element of, and you're saying x is greater than 0. Here's 0, greater than 0. So you see you're heading to positive infinity. So x is greater than 0, meaning starting at 0, heading to positive infinity, and also a round bracket there. Okay, remember it's a round bracket here because it's not equal to 0. At 0, there's an asymptote. And that is our answer. You can leave it like this or like that, and that's fine. Moving on to the next question. The last question for question 4, 4.6 says, describe the transformation of g to h if h of x is equal to this. Okay, let's look at g. Remember g, right? That was minus 9 over x and then plus 3 over 2. How did it become this? Yeah, you see the real challenge is, okay, of course, that negative, which is a big part of it. And of course, this is negative 3.5. Let's just rewrite that as an improper fraction. So 3.5 is 7 over 2, okay? So this is actually negative 7 over 2. We'll see what happened. Okay, so the first thing that I noticed is that looking at g, this was negative, okay? But now it's positive. So the only way you could have changed that is if you multiplied this, okay, or really just g, by a negative 1. And the reason I say g is because if you multiply this by negative, it's going to have an effect on this because this stands for g of x. So this is the y value of g, given that you know what x is. Okay, so it's the general y value of this graph for every x value. So if you take this and you multiply this by negative 1, look at what happens. It has two terms, so I have to use brackets. So negative multiplies in here, then it will become positive 9 over x. And then it multiplies in here, and that will become negative. And then we can take it from there and see what actually happened after that. Okay, so what happened is we took this g, right? And we multiplied it by negative 1. We made this negative, and we'll speak about what that means. But let's apply it first. So it means h of x, this is not h of x yet, but we first just took it, and of course we said minus g of x, and then that has an effect on this. So it multiplies in, like I showed, to become positive 9 over x, and then multiplies to that one to become minus 3 over 2. Okay, and so now we're looking at this and asking, how did we go from this to get to this equation? Okay, just remember the negative 3.5 is actually negative 7 over 2. So these two are already the same. The only difference is this, okay? From negative 3 over 2 to negative 7 over 2, what did we do? Okay, at this point, yeah, you can look at them as their decimal form. It's easier to look at it like that. This is actually 1.5, remember, okay, 3 over 2. So negative 1.5. So from negative 1.5 to negative 3.5, what did we do? You must have said minus 2. Okay, negative 1.5 minus 2 is negative 3.5. So what they did to this graph to form h was say minus g of x and then minus 2. And then that's what created that. So minus 2. And now do you see we have 9 over x minus 3.5. And that's how we got to this graph of h. And now comes the explaining, because we have to describe the transformation. We can see algebraically what to do to get to h of x, but what does this actually mean? What does negative g of x mean? Well, you're taking g of x, which stands for the y values of the graph of g. And you're taking those y values and you're multiplying them by negative 1. We can look at this as a single point, okay? And we can just take that point that was already on g. This point, negative 2 and 6, let's take that point and let's see what happens when you multiply its y value by negative 1. So that was negative 2 and 6. If you take this and you take the y value, okay, g of x, all the y values of g get multiplied by negative 1, you see that you're going to end up with a negative 6. So this point is going to be negative 2 and negative 6. So what did we do from this point to get to this point? Well, you saw we multiplied. We didn't shift it down, okay? So because we multiplied, it's not a shift. Instead, it's a reflection. So we took this and we reflected it across the x-axis. That's why you can see this point, okay? From the x-axis, it's exactly 6 units up, okay? From the x-axis, because you see the y value 6. And then the reflection is exactly 6 units down. It's a reflection across the x-axis. So we understand what that is now. Okay, so the graph of g was first reflected across the x-axis. Then what happened? And then we had to say a minus 2 to it. But you're saying minus 2 to negative g of x. Negative g of x would stand for the new values of y after you've reflected it, because g of x stood for the y values of g. So if you take the y values of a graph and then you say minus 2 to them, what's going to happen to that graph? Again, we can look at the point, okay? So if you can take this reflected point and then you say minus 2 to the y value, it's going to go minus 2, so minus 7 and then minus 8. This is going to be negative 2 and negative 8. So what did we do to this? Well, we directly subtracted a 2 from the y value. So you literally shifted this graph down by 2 units, or really this point down by 2 units. So it was shifted down by 2 units. So we can see the transformation that took place. It was first reflected across the x-axis and then shifted 2 units down. And that is our answer, okay? So it was reflected and then you can say to obtain h. Okay, so that is what happened to that function. And that is the last question for question 4. Question 5 says, given h of x equals 2 to the power of x minus 4, so we have an exponential equation. And 5.1 says, calculate the x-intercept of h. So to find the x-intercept of a function, you simply make y equal to 0. So h of x, that is y, so we'll say 0 equals 2 raised to the power of x minus 4. And then we can transpose the negative 4. So positive 4 equals 2 to the power of x. Make the bases the same. 2 to the power of 2 equals 2 to the power of x. And then equate the exponents. X is equal to 2. And that is our answer. They didn't say write it as a coordinate, so you can leave it like that. That is fine. Moving on to the next question. Question 5.2 says, calculate the y-intercept. Yeah, you already know they're going to ask you to draw the graph. So with this, the y-intercept is found where x is equal to 0. Okay, it's that point where x is equal to 0. So make x equal to 0. So in place of x, we say 0 equals, and that's 2 raised to the power of 0 minus 4. Anything to the power of 0 is equal to 1. So that's 1 minus 4, which is equal to negative 3. Okay, so your y-intercept is y equals negative 3, and that is our answer. Next question. The next question, 5.3, says, hence, sketch a graph of h on a system of axes, clearly showing the intercepts with the axes and the asymptote. Okay, we have our intercepts. The only thing we need to find is the asymptote. So what is the asymptote of this function? It works the same way as a hyperbola. The only difference is this one has one asymptote, and it's a horizontal asymptote. So you see how the horizontal asymptotes equation in the hyperbola is y is equal to q? It's the same thing here. The equation of an exponential function is in the form of y equals a multiplied by b raised to the power of x minus p plus q. Okay, because sometimes it's a shift, but don't worry, in grade 10 they barely ever include that shift. In grade 11, we work more on that. Okay, so it's going to be whatever was added to that. Okay, so there's our base and our exponent, and then it's minus 4. So we know it's simply y equals minus 4. That is the asymptote. Okay, now we can draw our graph. So just go ahead and put down a y-axis and an x-axis, and I know this goes down to minus 4, so yeah, I can just leave it like this. Okay, and so you're going to put a line down for minus 4. Okay, it's a dotted line because this is an asymptote, y equals negative 4. You can either write the equation or show that this line passes negative 4 on the y-axis. Okay, and then let's go ahead and figure out what this graph looks like. So there's certain things that will tell you the shape of the graph, and it's really just this part. That part you just use for your asymptote. So the 2 to the power of x will tell you what your graph looks like. Remember how it is a multiplied by and then b and then to that exponent, right? The value of a is whatever is in front of that base and that exponent. So the base and exponent is 2 and x. And so the number in front of it is actually an invisible 1. It's a positive number. A is greater than 0. And so what this means is wherever your asymptote is, your graph is going to lie above the asymptote. Okay, it's not going to be below here, it's above here. So an exponential function, it could either be increasing or decreasing. And the way you find out is by using that base and that exponent along with that number in front of it. In this case, it's just 2 to the power of x we're working with here. You're just going to find out whether it's increasing. Okay, so you can substitute. In this case, you can clearly see it's increasing. It's 2 to the power of x. So as x increases, your full y value will definitely increase. But if you wanted to just check for a graph that looks a little more complex, you can just substitute two x values. Okay, try x is equal to 1 and x is equal to 2, and then check the y value that you get. If we substitute 1 in place of x here, 2 to the power of 1 is 2. Okay, if you substitute 2 in place of x, 2 to the power of 2 is 4. And then just look at the first point and the second point and see what the y value did. Did it increase or decrease? It increased. Okay, so it means that your function is an increasing function. Okay, so we know that now. And now we know what our graph looks like, basically like that. Now you can put down your intercepts. We had an x-intercept of x equals 2. So on your graph, go on the x-axis and look for 2. So that's 2 over there. And then we had a y-intercept of minus 3. So minus 3, I'll just put that here, minus 3. And you know your graph is going to go up like that. And so you just sketch your graph. And there we go. Okay, so our function, that is called h. And that is the graph of h. And that's what it looks like. Moving on to the next question. Question 5.4 says, write down the point of intersection between y equals 2 to the power of x minus 4. Okay, so that is our graph of h. And y equals 1 over 2 to the power of x minus 4. And this is for 2 marks. So where will these graphs intersect? Okay, now because this is for 2 marks, you probably don't have to do much work. You can find it without actually thinking about it and just working with the fact that they said the point of intersection. So where will these two intersect? Okay, what is the point of intersection? So you would have to make them equal because you know that you're trying to find out where they intersect, which is where their y values are equal, okay, for the same x value, of course. So you have the choice to either equate these equations, y equals y and then 2 to the power of x minus 4, or you could think it through and it would take less work, just more thinking. So think about what this graph is, okay? It's y equals 1 over 2 raised to the power of x minus 4. It can be written in a way that we can easily compare it to this. And that is to take this 2 to the power of x in the denominator and then move it up to the numerator. When you do that, it's going to cause the exponent to become negative. So this is actually 2 raised to the power of negative x. Okay, now we're going to compare just like we did in question 4, okay? It's like a translation. How did we go from this to this? And really, what is the difference between these graphs? Do you see how they look identical? The only difference is this is a negative x and that's a positive x. So it means that here x is positive, here x was made negative. Meaning you can take this function and then if you just made the x values negative, then it will cause this function to be formed. Okay, so what does it mean to make the x values of a graph negative? In the previous question, we saw what it means to make the y values of a graph negative. So if you take a function and then you make the x values negative, let's just start with a single point. I'll take a point and let's just say it's 1 and 2. If I take this point and I make the x value negative, what happens? It's going to become negative 1 and 2. So if you plot that, that's negative 1 and 2. What happened to this point? We definitely didn't shift it because we multiplied negative 1 to the x value. So it means that this point was reflected across the y-axis to form this point. So that's actually what happened to these graphs. This graph was reflected across the y-axis and then it became that graph. Now you would have to think about what that would look like. If your original function looks like this, what happens when you reflect it across the y-axis? What is it going to look like? Do you see, for example, this point over here? The distance from this point to the y-axis is going to be the same distance from the y-axis to that reflection, okay, or that reflected point. Same thing over here, okay, this point, okay, same distance here, you go the exact same distance. And if you did that all through, you will see that you will form a graph, or really, let's just not stop there, let's continue till here. What will happen with this one? Well, it's already on the y-axis, so it's not going to be reflected over the y-axis, it's going to stay there. And then this point over here, if it's reflected, you see where it is, and then to the y-axis, it's going to have the exact same distance from the y-axis to that reflected point. So what's going to happen is you're going to have the same graph with the same asymptote that just looks like that. So the question is specifically, write down the point of intersection. Where would they intersect? They would intersect at that y-intercept, because when you try to reflect that over the y-axis, it's already -3 and 0. It's already on the y-axis. So if you reflect it across the y-axis, it stays there. In other words, the distance of that point from the y-axis is exactly 0 because it's on the y-axis. So the reflected point is also going to have a distance of 0 with the y-axis. Okay, so that is the point that we are referring to. It takes longer to explain, but it's much faster to think about. So what is that point of intersection? It is 0 and -3, the y-intercept. And that is our answer. And that is it for question 5. Okay, so that is the last question for this paper. I hope you guys enjoyed it. If you made it to the end of the video, well done on that. And if you have any questions, feel free to leave it in the comment section below, and I'll do my best to get to it as soon as possible. Hope to see you in the future videos.